Welcome back, guys. Today, due to um, many requests that I received from students in the class that they wanted to see another example of the shear and moment diagram. So I'm going to put up a typical structure here that most probably will tell all stories about how we go about drawing the shear and moment diagram. Okay, I'm going to start by giving you the structure. Let's say I have something like this. I have internal moment this way, 20 kilonewton meter, and I also have a roller here, and on top of the roller is a distributed load, something like this, with a value of the concentration at 6 kilonewton per meter. The drawing might not be to scale, but just bear with me on the numbers. And I'm going to call this as A, B, C, and also D. Okay, now the first order of the day, if you want to work on the shear moment diagram, is for you to get the reaction correct. So now let's go ahead and oops. So let's go ahead and draw the free body diagram again. So you have this beam, and I will have a y and also have a x. There's nothing on B except the moment. I'm going to redraw it just like that, and it's going to be the same thing. And right here, because of the distributed load, I'm going to have the resultant force coming in. I'm just going to put it something like this, and this is going to be 1/2 or 6 kilonewton per meter times the distance of 3, and that will give me 9 kilonewton resultant coming from that distributed load. So let's go ahead and do the equation of equilibrium. And I do my summation of forces in the x direction, and I know in equilibrium is going to be 0, and I have AX is equals to 0. And now let's do summation of moment at point A, and call it that as positive. I have at A, I have a 20 kilonewton, and that is in the positive direction. And I also have, yeah, mess it up. I should have CY here. So I have CY, and that's pointing in the positive direction as well. And the distance is 6 meters. And I also have the reaction from the uniform loading of 9 kilonewton, and the distance is actually 1/3 from here, and this is going to be 1, and the rest is 6. So I have 6 plus 1, so that's going to be 7 meters, and the whole thing is going to be 0. And if I solve for CY, so I have 6 CY plus 20 minus 63 is going to be 0, so my CY is just 63 minus 20 divided by 6, and we do a crunching real quick, and that's going to be 7.1667 kilonewton. So this is CY. Okay, once I get CY, I can do the summation of forces in the y direction, and in equilibrium, then that's going to be equal to 0. So I have my AY pointing up. There's nothing at B, and I have my CY going up, minus my resultant from the uniform loading of 9 kilonewton, and that's going to be equal to 0. And CY is 7.667, so my AY is going to be 9 minus 7.1667, and that is going to be 1.833 kilonewton. So I have AY and also CY, and let's go ahead and do the shear moment diagram. Once we have the resultant, I'm going to draw a nice line here. Oops. Okay, and this is going to be shear. My shear is in kilonewton, and this is actually the x-axis. We're moving from the left to the right, so I'm gonna indicate again all the points. So I have my B. Somewhere here, and I also have my C, and lastly I have my D. So this is actually all the areas that I want to concentrate. This is A, B is here, C, D. So now what happened at A, I have my AY is going up at 1.833, so I'm going to go up the scale. This is going to be 1.833, and so this 1.833 shear is going to level out because you don't have anything, no forces acting on it until B, and at B you have the internal moment, but that's not going to change the shear, so I will go ahead and continue at 1.833 until I reach C. At C, what I have is I have 7.1667 going up. So I'm going to take up the scale again, going up the distance of 7.1667. That will bring me up to 9 kilonewton. And from there, I need to go down to D, and I know this is my slope at 9 kilonewton, and I know my okay, we know very well that you have you have dv over dx, and that's going to be negative w, which means that your changes in shear is going to be the integral of that uniform loading, and that brings me up to see that unit. If this is 9, and I have um, my uniform loading here is actually a linear, and that is x. So I will have my shear, the derivative of that is going to be x squared. So I know it's going to be parabolic, and it will go down to 0. Change it to blue again. Okay. And this is going to be a parabolic, something of a function of x squared. And this 9 here is actually the area of the triangle over which the loading is, which is 9 kilonewton. So this is basically your shear diagram for that particular loading. Now let's go ahead and do the moment diagram. So my moment is going to be in kilonewton meter, and I know at point A I have no moment, and I will start with 0 here. And how much do I go up on the scale? Okay, now it's very easy. I have the area here, this area here, because dm over dx is equals to v, and your whatever delta m is, the differential moment is simply the area of your shear diagram. So the area of the shear diagram is 1.833 times 2, and this is 3.6667 here. And so I go up to, it's going to be 3.6667 here, and it's going to be a linear going up. At this juncture B, I also have the internal moment. As you can see, the internal moment here is 20, and it's pointing this way. So I know it's going down, and I will go down from 3.667, the value of 20. So I go down the scale, that will bring me up to minus 16.33, which is 20 minus 3.667. So that is my moment at point B. And I also know that this area here is going to be 1.833 times 4. This area here is 7.332, and I will go up from 16 to a point where 16.23, I will go up 9 to 9, because I take 16.332 and minus 7 will bring me up to 9. So my moment diagram is going to be something like that. And from here, I need to know what is the area here, and the area for the parabolic is given by 1/3 of b times h, and I have 1/3 my B is base is 3 and my height is 9. So that will give me 9 um, kilonewton meters here. So that's the area under the parabolic, and this 9 is actually this 9 here. So now we know very well just now that this is x squared. So when I go into my moment, it's going to be x cubed. Okay, so my moment diagram is going to be something with x cubed, so it's going this way. Okay, and it goes back to 0. And so this is your moment diagram that I shaded here. So I hope that will explain a little bit about the shear and moment diagram of a beam with an overhang and also a variable distributed load. So until we meet again, most probably I'll have another one of the shear moment diagram for you to see. Talk to you guys later. Bye bye.